Section 15.9, Change of Variables and Multiple Integrals. So far, we've switched coordinates from Cartesian to polar, to spherical, to cylindrical. So how about we talk about what it means to change coordinates, change of variables in general. A change of variables is given by a transformation t from the uv plane to the xy plane. T of uv is equal to xy. So we take uv coordinates and we make them into xy coordinates. So x and y are related to uv by the equations x is some function of uv and y is some function of uv. We call them g and h, but it doesn't really matter what you call them. We usually assume that t is a C1 transformation, which means that g and h have continuous first-order partial derivatives. A transformation t is really just a function whose domain and range are both subsets of R2, the plane. So if t of u1 v1 equals x1 y1, then the point x1 y1 is called the image of the point u1 v1. If no two points have the same image, t is called 1-to-1. Our figure shows the effect of a transformation t on the region S in the UV plane. So here's our region S. T goes from S to the xy plane and results in some image R. So it transforms S into region R in the xy plane. It consists of all of the images of all the points in S. If t is a 1-to-1 transformation, then it has an inverse transformation, t inverse, from the xy plane to the UV plane, and it may be possible to solve for u and v in terms of x and y. So in that case, we would write u as capital G, function of x and y, and v as capital H, function of x and y. That's when we go backwards from xy to uv with t inverse. So as an example, we have a transformation defined by the equations x equals u squared minus v squared, y equals 2uv. Let's find the image of the square s equal to uv such that u is between 0 and 1 and v is between 0 and 1. So how about we first try drawing the square in the UV plane. So here's u, here's v, and I need a square, so let's say this is my square. This could be 1, 0, because u goes all the way up to 1, starts at 0, and then this could be 0, 1, because v goes up to 1, and this is 1, 1, where they're both 1. So how about I call this side S1, I'll call this side S2, call this side of the square S3, and this one S4, and I'll look at what happens as each side gets transformed into the xy plane. So how about I draw the xy plane? So put that over here. So here's x, and here's y. Let's look at what happens to our first side. We'll call that S1. Notice that S1 is the line segment that goes from 0, 0 to 1, 0. So we could describe that just by saying it's the line segment v equals 0, where u is between 0 and 1. So that means that when we convert it to x and y coordinates, remember x is u squared minus v squared, v is 0, so x is just u squared. And then y is 2 times uv, so v is 0, so y is 0. And since x is u squared, u goes between 0 and 1. This means that x goes between 0 and 1. So that means in the xy plane, we get pretty much the same line segment. Just goes up to, let's say over here is 1, 0. So then I'm going to draw an arrow to indicate that this line segment gets mapped onto this line segment. So now let's check out S2. So for S2, again, it's a line segment. In this case, u is constant 1. Our first coordinate is constant 1. And it's v that varies between 0 and 1. So I'll write that. So u is 1, and v goes between 0 and 1. So then I plug that in, u is constant 1, so x is 1 minus v squared. And then plugging u equals 1 in here, I get that y is 2v. So what I can do is I can eliminate my parameter now to solve for x and y just in terms of x and y, because notice this is just the xy plane, there's no u's or v's. So if I want to be able to graph it, I need x and y without any u's or v's. So I could say that since y is 2v, that means that y over 2 is equal to v. So x is 1 minus y over 2 squared. So that's the same as 1 minus y squared over 4. So v goes between 0 and 1. That means that this goes between 0 and 1, so plugging in 0, plugging in 1 gives us 1 and 0, so x still goes between 0 and 1. So that means that x is the 1 minus y squared over 4 parabola between 0 and 1. So graphing that looks something like this. Now we, by the way, just here are the arrows that map it. So this line segment over here, S2, it maps onto this parabola over here. Okay, let's do S3 now. So for S3, we have u going between 0 and 1, and v is constant 1. So that implies, when we plug in, that we get that x is u squared minus v squared, so x is u squared minus 1. Y is equal to 2u. So again, we eliminate our parameter. U is y over 2. That means that x is y squared over 4 minus 1. This time, if we plug in 0 and 1 for u in order to see what x goes to, it looks like x goes from minus 1 all the way up to 0. There's no way that x could get up to 1. So that means that it's the parabola y squared over 4 minus 1, but from minus 1 to 0. So that looks something like this. And over here is minus 1, 0. So that's for S3. Okay, last but not least, we'll do S4. And S4 is this segment over here where it looks like u is constant 0 and v goes between 0 and 1. So similar to S1, this means that x is minus v squared, y is 0 again, and this means that x goes between minus 1 and 0. So that's just this last remaining piece, which is nice, all fits together. So that's for what we get when we map S4. So we can call this S, and we can call this R, our region in the XY plane. Okay, as I hinted at, the whole point of this is to be able to integrate. So in order to do that, we need to talk about what it means to have the Jacobian of the transformation t. So in shorthand, we use this notation, partial xy over partial uv, and what that means is you take the determinant of this matrix where the top two rows are partial x with respect to u and v, and the bottom two rows are partial y with respect to u and v. So then you remember cross multiply and subtract, and you get this. So what we're going to do is we're going to briefly show that the change of variables in a double integral results in an integral where you convert from x to some x in terms of u and v and some y expressed in terms of u and v. You multiply by the absolute value of the determinant of the Jacobian, and you just integrate with respect to u and v. So let's do this real quick. So we'll start off with some region in the UV plane. So let's see if I can draw that. So here's U, V, and we're going to draw some rectangle S. Okay, so then let's call this point U0, V0. And we'll call this our change in V, delta V, because over here, notice U is constant. So if I want an equation for this line is the line where U is just, equal to U0, the constant. U0 is our variable, U0 is our constant. Like when you had an x equals line, it was a vertical line. So then over here can be my change in U, and over here is my line from left to right that's like a y equals line, so this will be V equal to constant V0, the y value over here. Let's look at what happens when we transform this. So we'll apply our transformation t, we'll end up in the xy plane. So we'll have some point x0, y0, and then this v equals v0 becomes something else. It doesn't have to be straight, so I'll make it nice and curvy, because why not? And we end up with something sort of like this, our region R. So it's not quite a rectangle, it could be almost any shape, whereas we have this U0, V0 goes to some other point, let's say x0, y0, somewhere. And how about we come up with a vector, position vector, that points to these lines over here. So we'll call that R of uv. So then R of uv is some function of uv I plus some function of uv j, and that's just going to be the position vector that points to each point in R. So it points to this point, points to that point, points to every point. So that means that this line segment over here is the position vector where we take u and make a constant u0. We let v vary. And this position over this kind of piece over here is where we let u vary, and we set v to be constant v0. So that means this piece becomes this thing using r, and this piece becomes this thing using r. So in order to try to come up with an approximation for this area in terms of, let's say, derivatives, let's take a look at what we get when we take the partial derivative of r with respect to u. So that's the partial derivative of g with respect to u of u0, v0, because what I'm going to do is I'm going to do this at this point, x0, y0, so that I can kind of build up some vectors to approximate the area of this thing. So I'm doing it at u0, v0, so this is ru at v0, u0, v0, and this is our partial derivative with respect to u. Just wrote v0 twice. So notice this is just partial of x with respect to u times I plus partial of y with respect to u times j. And we get pretty much the same thing if we want the partial with respect to v. Just gv at u0, v0 plus hv at u0, v0, and that's just going to be our partial of x with respect to v plus our partial of y with respect to v. So I would like to take a closer look at this region R over here. So how would I draw it? Like over here. Need a little more space. Okay, so this is my R. What I would like to do is I would like to come up with some vectors over here and over here. Oops. So that I can make a parallelogram to approximate my area of this rectangle. So we'll call these vectors A and B. Okay, remember this is our position vector R at U0, V0. That points to this point right over here. So that means that this point over here is R at U0, where we let V vary across over here until it goes up some value delta V. Because remember, delta V was how much we were traveling up over here until we get to the end. So that means that this endpoint over here is the result of the vector R pointing at what we get when we plug in U0 plus delta U. We let U vary and keep V fixed. So if I want this vector A, I can get that just by subtracting by these two guys, because there are those 2 points at the ends, which is how we find position vectors of points. So I have vector A must be equal to R of U0 plus delta U V0 minus R of U0 V0. And that means that similarly vector B must be equal to R of U0 V0 plus delta V minus R of U0 V0. Remember also, we computed the partial with respect to U. So let's look at that in terms of these guys. Remember, by definition, that's just the limit of these secant. So that's the limit as delta U goes to 0 of R of U0 plus delta U V0 minus R of U0 V0. So it's basically the limit of A over delta U. So this means that if I want to look at just R of U0 plus delta U V0 minus R of U0 V0 means I just want to look at vector A. I could approximate A by multiplying both sides by delta U. Obviously the limit makes a difference, so I'm just saying this is an approximation. It's not equality, but still it's a decent enough approximation if I make this a small enough piece. Similarly, we get that the vector B can be approximated. So R of U0 V0 plus delta V minus R of U0 V0 is approximately delta V times R of V. So let's see if I can put these in there. It kind of looks something like this. I've got, this is a delta V, RV, and then over here would be my delta U, RU. Don't like the way that came out. Let me try a little better. Okay, and I'm going to make a parallelogram out of this. So something roughly like this. And I use this parallelogram that I made to approximate the area formed by the vectors A and B, which approximates the area of R. So that means this parallelogram is an approximation for the area of R, if I get the area of that parallelogram. But getting the area of that parallelogram is fairly easy for us, right? Remember, the area of a parallelogram, as we saw in section 12.4, is just the cross product. So I can say that the area of R is approximately the magnitude of delta U RU cross with delta V RV, and that's, well, these guys are constants, so I'll pull them out. So we just get RU cross RV times delta U delta V. So let's see what RU cross RV is. So RU cross RV is equal to the determinant of the matrix formed with I, J, and K, where, remember, we calculated RU was these partials and RV was these partials. So I'll just throw those in. So we have partial X with respect to U, and we have partial of Y with respect to U. And then for V, we have partial of X with respect to V and partial of Y with respect to V. And then K is 0 because we're in 2 dimensions. So then, because K is 0, what I can do is I can take just K times this determinant, and then 0 times this one will kill it off, and then 0 times this one kills that one off. So all I have to do is take one determinant. So I have partial X partial U, then partial Y partial U, partial X partial V, partial Y partial V, K. But notice that this is this times this minus this times this. So because I'm multiplying these guys anyway, and multiplication is commutative, I could just put this one over here and put this one over here, just switch the order. So that means this is the same thing as partial X partial U, but I switch partial Y partial U with partial X partial V just to keep all my X's on top. It's just a convenience in our notation. So I'll end up with X's on top and UV's underneath. Y's on the bottom, UV's underneath. Which is exactly what we wanted to show, right? That the delta A is approximately the absolute value of the determinant of our Jacobian, which is what we just calculated, times delta U delta V. So let's do an example of this. Let's use the change of variables x equals u squared minus v squared, y equals 2uv to evaluate the integral, double integral of y dA over r, where r is the region bounded by the x-axis and the parabola is y squared equals 4 minus 4x and y squared equals 4 plus 4x, where y is greater than or equal to 0. Notice this is the same region we were just looking at in the previous example. We have x equals u squared minus v squared, y equals 2uv, same as before. These parabolas are what we got when we looked at the region. We just didn't have y squared by itself. We had them x equals. So in this case, they just solve for y squared, but it's the same region. First, we need to check out our Jacobian. So that's partial of xy over partial of uv. So we write that as the determinant of the partial of x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. Okay, so let's take partials of these guys. X with respect to u, notice v squared is constant, so it's just 2u. Then we want x with respect to v, so that's minus 2v. Then y we look at with respect to u, so that's just 2v, because those are constant. To be a little bit careful, this is a 2, and this is a partial. So I'll make that tail a little bit longer maybe. This is 2v. And then this last one is 2u. So we take that determinant, we get 4u squared, multiplying our diagonals and subtracting minus minus is plus, so plus 4v squared. Notice this determinant is always positive. We have to take the absolute value of our determinant when doing our integral, but we don't have to really worry about that because this is always positive. So let's plug into our change of variables formula now. We have the double integral over r y dA equal to the double integral over s in the uv plane. And we just have to plug in for y, so y is 2uv. And then we have to throw in our Jacobian. So it's a good thing we computed that over partial uv. And we end up with the integral from 0 to 1, the integral from 0 to 1 of 2uv, because remember, in the uv plane, this was just a rectangle when we drew it, and we have 4 times u squared plus v squared because I'm factoring out the 4. And now we have du dv. So doing our integral, we get 8 times the integral from 0 to 1, 0 to 1, u cubed v plus uv cubed du dv, which is 8 times the integral from 0 to 1 of 1/4 u to the 4th v plus 1/2 u squared v cubed from u equals 0 to u equals 1 dv. So that's just the integral from 0 to 1 of 2v plus 4v cubed dv, which is v squared plus v to the 4th from 0 to 1, which is 2. So notice that this resulted in a very easy integral, because integrating over a rectangle is way easier than integrating over some region bounded by these x equals parabolas. But that was because they gave us the change of variables formula to use. And very often we won't have that. We'll have to come up with a change of variables formula ourselves. So let's do an example of that. Okay, notice in this case we have to evaluate this double integral. It's a mess, and are some trapezoidal region, but they didn't give us the change of variables. However, maybe this seems a little bit natural. If we make this equal one variable and this equals the other, hopefully it'll work out. So let's set u equal to x plus y, and we'll let v equal to x minus y. So notice these are u functions of x and y, v functions of x and y. So this is t inverse. This is going backwards. What we usually like to do is go from uv to the xy plane. That's when we have x as a function of u and v and y as a function of u and v. So that way we can replace x and y. So in order to solve for x and y, what we can do is we can say that, let's say v plus y is equal to x. And then we can replace x with v plus y, and that way we could solve for y in terms of just u and v. We could see y is half of u minus v. And then we can similarly solve for x, and we get that x is equal to half of u plus v. So this is our transformation t. This goes from the uv plane to the xy plane. So let's see if we can take our Jacobian, because we're going to need that. So partial of xy over partial of uv, and that's partial x with respect to u, partial of x with respect to v, partial of y with respect to u, partial of y with respect to v. So that's the determinant. Well, this is going to be a half. Looks like they're pretty much all 1/2, except for this last one with v where there's a minus. So we have half for each of our partials, minus a half for the one with respect to the one of y with respect to v, and taking that determinant, we see that that's minus 1/2. Half times minus 1/2 minus half times a half. Okay, so that's our Jacobian. That'll be helpful when we want to plug in. How about we now take a look at what our regions will look like when we transform them. So we're going to go from the UV plane to the XY plane via transformation T. But we started with u equals functions, so that was T inverse from this XY plane. Okay, so let's see what everything is. We'll go off of T inverse, because we were given the region R. So we'll build the XY region first, and then we'll see what that looks like in the UV plane. So first we have, well, let's see. How about we try drawing our region first? We have these vertices, so we'll put those in. So we have 1, 0 is over here. We have 2 zeros over here. We have 0, -2, and 0, -1, so that's like over here and over here. So our region is this trapezoid over here when we connect it all. So we can call that R, where this is 1, 2, -1, and -2. So let's see if we can come up with equations for each of these things. Okay, well, notice this is just going to be where y is 0. And then I need another equation. How about for this piece over here? Well, that's just the line with intercepts 2 and -2. So I could say that that's the line x minus y is equal to 2. You could also just say that that's y equals x minus 2, if you like, because it goes up 1 over 1 and starts at -2, but however you like. So that's another piece. I got 2 more pieces to do. How about this one? That's easy. That's just where x is 0. And I got one more line that I've got to come up with. And again, it has slope 1, but it has intercepts 1, -1. So I could say this is x minus 1 equals 1. Now let's see what happens when we transform this in the UV plane. So if I plug in y equals 0, I see half u minus v is 0. So half u equals half v, so u equals v. So that's from 1 to 2, because this is going from 1 to 2 in x. So I should have it somewhere over here. So this is our piece that corresponds to this piece. U equals v. Okay, so this is the point 1, 1. Because you plug in y equals 0 and x starts at 1. And you get u equals 1. Do the same thing for v. You get v equals 1. And that means that over here also we get 2, 2, when we plug in 2 for x. So now let's look at our next piece. When x minus y equals 2, well, v is literally equal to x minus y, so that means v equals 2. And then we can draw v equals 2. We're doing that from, it looks like minus 2 to 2, because for our next piece, we're going from 2 to minus 2, minus 2 to 2. So that's like this piece over here, v equals 2. And that corresponds to this piece. Okay, for our next piece, we have x equals 0, so plugging that in, we get u is minus v. So that gives us this. And that corresponds to this piece right over there. And last but not least, we have v equals 1, because x minus y is 1. So that completes our trapezoid nicely. And we could say that that's this piece corresponding to this one. We can call this S, and there we have our region. So this is v equals 1. Okay, so we can describe S, it looks like, as the set of points uv such that v goes between 1 and 2. Because these are just constants, it looks like it's easiest to do this as a type 2 region. You could think of, if you were to think of this in the xy plane, where our v is going to be between our constant limits, and it looks like we have functions in the left and right, so we'll go from left to right when we integrate. So u goes from minus v on the left to v on the right. So now we can do our double integral. Because we have our Jacobian, we have our region, we can see that our double integral over r of e to the x plus y over x minus y dA is equal to the double integral over s of e to the u over v times the absolute value of our Jacobian, determinant of our Jacobian, and du dv. So that's from 1 to 2 for v, that's what we said, and then minus v to v for u, e to the u over v, times the absolute value of minus 1/2 is 1/2 du dv. So that's 1/2 times the integral from 1 to 2 of v e to the u over v from u equals minus v to u equals v dv, which is 1/2 times the integral from 1 to 2 of e minus e to the minus 1 times v dv, which is 3/4 e minus e to the minus 1. So it results in a pretty easy integral, even though it was a lot of setup work. Notice the original integral. That would have been a pain if we hadn't converted this. Just like in 2 dimensions, we have a 3-dimensional change of variables. So that's a change of variables in a triple integral. So our function is actually in the 4th dimension, but that's okay. We're going to take the determinant of this Jacobian. So we just add an extra row and column. Now we have an extra variable w, extra variable z. So we take partial of x with respect to w also on top. And for our last row, we have an extra partial z with respect to u, v, and w. So our change of variables in triple integral is pretty much the same as double integral, just with that extra z and the extra w. So we have just to integrate with respect to w now. So how about we use this to derive the formula for triple integration in spherical coordinates. Remember, in spherical coordinates we have x equals rho sine phi cosine theta, y equals rho sine phi sine theta, and z is rho cosine phi, because it was r cosine theta and r sine theta, but r we said was rho sine phi. So it would be helpful now if we got the Jacobian. So let's do that. So partial of x, y, z with respect to rho theta phi is equal to the determinant. Let's put sine phi cosine theta, because that's the partial of x with respect to rho. Notice that means that sine phi and cosine theta are constant, so those are the only things that we have remain. Then we want the partial of x with respect to theta. So notice that's just, this is the only thing that has our function. This is just constant, so derivative of cosine is just minus sine, so we end up with minus rho sine phi sine theta. And lastly, we take partial of x with respect to phi, so that's just cosine, so we have rho cosine phi cosine theta. Okay, now let's do partial of y with respect to each of those guys. So for y, we get sine phi sine theta when we take the partial with respect to rho. Then partial with respect to theta. For y, we get rho sine phi cosine theta. Then we take the partial with respect to phi, and we get rho cosine phi sine theta. Lastly, we'll take the partial of z with respect to rho, theta, and phi. So with respect to rho, that's just cosine phi. And then with respect to theta, there's no theta, so that's just 0. All constant. And then with respect to phi, it's just minus rho sine phi. So then this ends up becoming, let's see, how about we use the bottom row? You can think of that as moving to the top if you want, but I think it's a little bit easier to just take cosine times this determinant. That way we could take 0 times this determinant, so it'll just collapse, and then we'll take minus sine times this determinant. So we get cosine phi times the determinant of minus rho sine phi sine theta rho cosine phi cosine theta rho sine phi cosine theta rho cosine phi sine theta. So that's our first determinant minus, well, 0. So then minus rho sine phi times our last one. So that's sine phi cosine theta minus rho sine phi sine theta sine phi sine theta rho sine phi cosine theta. So we have to multiply our diagonals and subtract. So we do that. We get cosine phi times minus rho squared sine phi cosine phi sine squared theta minus rho squared sine phi cosine phi cosine squared theta minus rho sine phi times rho sine squared phi cosine squared theta plus rho sine squared phi sine squared theta. Okay, let's see if we can work through that entire mess. Well, we've got, it seems like a minus rho squared sine phi cosine squared phi in both of these guys. So we can factor that out, and we're just left with that times sine squared plus cosine squared theta, which is 1. So all we have left for our first guy is minus rho squared sine phi cosine squared phi times 1, which is minus rho squared sine phi cosine squared phi. And then for our other guy, we have a minus rho squared sine squared phi cosine squared minus rho squared sine squared phi sine phi, and then minus rho sine phi rho sine squared phi. So again, we just end up with cosine squared plus sine squared inside, multiplying by, so that's just 1. So all we have left over there is minus rho squared, because we have rho times rho. And then I'm going to write sine phi separate from sine squared phi. I'm not going to multiply them through because I want to keep the sine phi separate so I can factor that. So I'll have sine phi sine squared phi and times 1, so that's just itself. And then again, we've got minus rho squared sine phi in both of these guys. So all we have left inside is cosine squared phi and sine squared phi, which add up to get 1. So we just have minus rho squared sine phi. Okay, that's perfect because we know that phi is between 0 and pi. So that means that the sine of phi will always be positive for us. So that means that if we're looking at the absolute value of our Jacobian, the determinant of our Jacobian, that's the absolute value of partial xyz with respect to rho theta phi. So that's just the absolute value of minus rho squared sine phi. Rho is always positive by definition, and sine phi is positive for us now, so we just take the absolute value of minus 1, which is positive 1, so we end up with rho squared sine phi. Okay, so that's pretty beautiful because now we can rewrite our triple integral over R of f of x, y, z dv as the triple integral over S using our change of variables formula, where x becomes rho sine phi cosine theta, y becomes rho sine phi sine theta, z becomes rho cosine phi, and our Jacobian, we said when we take the absolute value, is just rho squared sine phi, and then we integrate with respect to rho, theta, and phi, which is exactly the same formula that we saw we had before.